The silence between stars is not empty. It is a question that has haunted astronomers for nearly a century, a puzzle wrapped in the vastness of 400 billion suns in our galaxy alone. And yet not a single whisper, not one flicker of unmistakable light, to suggest we are anything other than alone. This is the mystery that physicist Enrico Fermi once posed over lunch, a simple wondering that became one of science's most profound riddles. The numbers say the universe should be teeming with life, and yet the cosmos offers us only stillness. If these quiet explorations help ease the mind toward rest, subscribing means more of them will find their way to you. Now, as the night settles and thoughts grow softer, we can turn toward the stars and their strange, beautiful silence, and so the telling begins. Let us begin, then, with the sheer immensity of the night sky, and with the patient work of those who first attempted to count what had always seemed uncountable. When you look up on a clear evening, far from the glow of cities, you might see a few thousand stars scattered across the dome of the heavens, and this has been the human experience for as long as our species has gazed upward. But behind those visible points of light lies a vastness that took centuries of careful observation to comprehend, a depth of space containing so many suns that the numbers themselves begin to lose their ordinary meaning and become instead a kind of quiet poetry of scale. The Milky Way, our home galaxy, is a vast spiral of stars and dust and gas, stretching approximately 100,000 light-years from one edge to the other. And within this enormous structure there exists somewhere between 200 billion and 400 billion individual stars. That range, between 200 billion and 400 billion, reflects the genuine uncertainty that remains even today in our estimates, because counting stars is rather like trying to count grains of sand on a beach while standing at its center and looking outward through a gentle haze. We can see some stars quite clearly, while others are hidden behind clouds of interstellar dust, and still others are simply too faint and too distant to register on even our most sensitive instruments. The first serious attempt to understand this abundance was undertaken by a musician and astronomer named William Herschel, who in the 1780s began a systematic survey of the heavens from his home in England. Herschel, who had already achieved fame for his discovery of the planet Uranus in 1781, developed a method he called stargazing, in which he would point his telescope at different regions of the sky and carefully count every star visible within his field of view. By assuming that stars were distributed more or less uniformly through space, and by noting how the counts varied in different directions, he hoped to determine the shape and extent of what he called the sidereal system, which we would now recognize as the Milky Way galaxy. Herschel's method was imperfect, limited by the instruments of his time and by assumptions that would later prove only partially correct, but his work represented the first scientific effort to move beyond simply admiring the stars and toward understanding their true number and arrangement. He could not have known then just how many suns surrounded us, nor could he have imagined that our entire galaxy was merely one among countless others stretching outward into an observable universe far larger than anything his age could conceive. For much of human history, it was assumed that the Milky Way, that pale band of light stretching across the night sky, represented the entirety of the cosmos, and that the fuzzy patches called nebulae were simply clouds of glowing gas within our own stellar system. This understanding changed dramatically in 1924, when the American astronomer Edwin Hubble, working with the great 100-inch telescope at Mount Wilson Observatory in California, was able to resolve individual stars within the Andromeda Nebula and to determine, through careful measurement of their brightness, that this object lay at a distance of approximately 900,000 light-years, far beyond the boundaries of our own galaxy. We now know that distance to be closer to 2.5 million light-years. But Hubble's essential conclusion was correct, and it transformed our understanding of the universe in a single stroke. The Milky Way was not the whole of creation, but merely one island of stars among what appeared to be a great many others. As telescopes grew more powerful and surveys more comprehensive throughout the 20th century, the estimated number of galaxies in the observable universe climbed steadily, reaching figures in the tens of billions and then the hundreds of billions. But in 2016, a team led by the astronomer Christopher Kinselis at the University of Nottingham published a study that revised this number dramatically upward. By combining deep observations from the Hubble Space Telescope with mathematical models of galaxy evolution and distribution, Kinselis and his colleagues estimated that the observable universe contains approximately 2 trillion galaxies, a figure some 10 times higher than previous estimates had suggested. 2 trillion galaxies. Let that number settle quietly into your awareness, like a stone dropped into still water, its ripples spreading outward. Each of those galaxies contains, on average, something like 100 billion stars, though the range varies enormously from small dwarf galaxies with only a few billion stars to giant elliptical galaxies containing several trillion. When we multiply these figures together, we arrive at a number so large that it serves no practical purpose to write it out in full, but which might be expressed as something in the neighborhood of 1 septillion stars in the observable universe. That is to say, a 1 followed by 24 zeros, a quantity that the human mind can acknowledge but cannot truly grasp in any intuitive way. And this brings us to a question that has occupied the minds of scientists and philosophers and curious observers for generations. A question that seems almost inevitable when one contemplates the sheer abundance of suns in the cosmos. If there are so many stars, and if many or most of those stars have planets orbiting them, and if some fraction of those planets lie at distances from their stars where liquid water might exist on their surfaces, then where is everyone? Where are the other minds, the other civilizations, the signals and the artifacts that one might expect to find in a universe so richly populated with potential homes for life? This question was given its modern formulation during a summer afternoon in 1950, when the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory in New Mexico. The conversation had turned, as conversations among physicists sometimes do, to the topic of flying saucers and the possibility of visitors from other worlds. And Fermi, after thinking quietly for a moment, is reported to have asked simply, "Where is everybody?" The question became known as the Fermi Paradox, though paradox is perhaps too strong a word for what is really a puzzle or a problem. An apparent contradiction between the high probability that extraterrestrial civilizations exist and the complete absence of evidence that any such civilizations have ever visited Earth or made their presence known. 11 years after Fermi posed his famous question, a young radio astronomer named Frank Drake organized a small scientific meeting at the Green Bank Observatory in West Virginia, a facility nestled in a quiet valley where radio telescopes could listen to the faint whispers of the cosmos without interference from the electronic noise of modern civilization. The meeting was held in November of 1961, and it brought together just 11 attendees, a select group that included the young planetary scientist Carl Sagan, who would later become famous for bringing astronomy to the general public, and the physicist Philip Morrison, who had co-authored one of the first scientific papers proposing the search for extraterrestrial radio signals just 2 years earlier. Drake wanted to give structure to their discussions about the search for intelligent life beyond Earth, and so before the meeting began, He wrote on a chalkboard a simple equation that he had devised, an equation that would become perhaps the most famous mathematical expression in the history of astrobiology. The Drake equation, as it came to be known, does not provide a definitive answer to how many civilizations might exist in our galaxy, but rather serves as a way of organizing our thinking about the problem, breaking the great question into a series of smaller questions, each of which might be addressed through observation and scientific investigation. The equation begins with the rate at which new stars form in our galaxy each year, a number that modern observations have established to be somewhere in the range of 1.5 to 3 solar masses per year, which translates to perhaps 1 to 2 new Sun-like stars being born annually, along with a somewhat larger number of smaller, dimmer red dwarf stars. This figure is considerably lower than it was in the early history of the galaxy, when star formation proceeded at a much more rapid pace, but it provides a reasonable estimate for the present epoch and allows us to think about how the population of potentially life-bearing worlds might grow over time. The second term in the equation asks what fraction of those newly formed stars have planets orbiting them. And here our knowledge has increased dramatically in recent decades. When Frank Drake wrote his equation on that chalkboard in 1961, not a single planet had ever been confirmed to exist outside our own solar system, and estimates of how common planets might be varied wildly depending on theoretical assumptions about how solar systems form. But beginning with the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995, and accelerating rapidly with the launch of NASA's Kepler Space Telescope in 2009, our understanding of planetary abundance has been transformed entirely. The Kepler mission operated until 2018, monitoring the brightness of over 150,000 stars simultaneously and watching for the tiny dips in light that occur when a planet passes between its host star and our line of sight. Over the course of its mission, Kepler discovered more than 2,600 confirmed exoplanets, along with thousands of additional candidates awaiting verification, and the statistical analysis of these discoveries led to a remarkable conclusion. Planets are not rare curiosities but rather the common outcome of star formation, with current estimates suggesting that virtually every star in the galaxy has at least one planet orbiting it, and many stars have several. The next term in Drake's equation asks what fraction of those planets might be located in the so-called habitable zone, that ring of orbital distances from a star where temperatures would allow liquid water to exist on a planet's surface, neither so close that water would boil away into the vacuum of space nor so far that it would freeze permanently into ice. The boundaries of this zone depend on many factors, including the luminosity of the host star, the composition of the planet's atmosphere, and the presence of geological processes that might regulate climate over long periods. But careful analysis of the Kepler data and subsequent observations have allowed astronomers to make reasonable estimates. In 2020, NASA released a study suggesting that there may be as many as 300 million potentially habitable Earth-like planets in our galaxy alone, defined as rocky planets of roughly Earth size orbiting within the habitable zones of Sun-like stars. This number is, of course, highly uncertain, and it does not account for many other factors that might affect habitability, but it gives us a sense of the raw abundance of worlds where conditions might, at least in principle, permit the existence of life as we understand it. 300 million worlds in our galaxy where liquid water might pool in oceans or flow in rivers, where the temperatures might allow for the chemistry that we associate with living things. And our galaxy is just one among 2 trillion others scattered across the observable universe, each with its own hundreds of billions of stars, each of those stars potentially accompanied by its own family of worlds. These numbers are worth dwelling on, not because they provide answers, but because they establish the foundation upon which the great puzzle rests. The stars appearing overhead on a clear night are not merely points of light but distant suns, each one a furnace of nuclear fusion burning steadily through the cosmic ages, many of them accompanied by worlds that we have never seen and may never visit but which nonetheless exist, circling patiently in the darkness. And somewhere among all those worlds, across all those galaxies, through all those vast and silent distances, the question remains, quiet and persistent and unanswered, as the stars come out one by one and the universe settles into its ancient stillness around us. In the summer of 1950, in the high desert of northern New Mexico, a group of physicists walked together toward lunch, their conversation drifting pleasantly from one topic to another as conversations among friends often do. The town of Los Alamos sits at an elevation of more than 7,000 feet, perched on a series of finger-like mesas that extend from the Jemez Mountains, and the air there is thin and clear, carrying the scent of pine and the particular dryness of the American Southwest. The laboratory itself had been established less than a decade earlier, carved out of a former boys' school to serve as the secret headquarters of the Manhattan Project, and by 1950 it had settled into a somewhat quieter existence as a center for ongoing nuclear research, though the weight of what had been accomplished there still lingered in the institutional memory of its hallways and its people. Enrico Fermi was walking that day with three colleagues, Emil Konopinski, Edward Teller, and Herbert York, and their path took them along one of the narrow roads that connected the laboratory buildings to Fuller Lodge, where meals were served in a large rustic dining hall built of enormous logs. The summer sun would have been intense at that altitude, but the air remained cool enough to make walking pleasant, and the four men moved at an unhurried pace that suited both the midday heat and the leisurely nature of their discussion. They had been talking, as it happens, about a cartoon that had recently appeared in the New Yorker magazine, a publication that circulated even in that remote scientific outpost and provided a connection to the wider cultural world beyond the security fences and the classified work. The cartoon in question depicted a group of aliens, small green figures of the sort that had become familiar in popular imagination, and these extraterrestrial visitors were shown making off with municipal trash cans, the implication being that a recent spate of missing garbage receptacles in New York City might be attributed to interplanetary mischief rather than ordinary theft. It was the sort of gentle absurdity that the New Yorker specialized in, a wry commentary on the flying saucer craze that had captured American attention in the years following the Second World War, and the physicists found it amusing in the way that intelligent people often find amusement in the collision between popular fancy and scientific sensibility. The conversation wound its way through the implications of the joke, touching on the question of extraterrestrial life and the possibility of visitors from other worlds, and it was in this context that Fermi made the remark that would eventually bear his name. They had reached the dining hall and taken their seats, the conversation still continuing in that easy manner of colleagues who have known one another through years of intense collaborative work, when Fermi suddenly asked, in his accented English that retained the rhythms of his native Italian despite decades of living in America, "Where is everybody?" The question emerged from no particular immediate prompt, as though Fermi had been calculating quietly in his mind while the others talked, and it carried a weight that the lunchtime setting belied. His companions understood immediately that he was not asking about the other diners in Fuller Lodge, nor about absent colleagues who might have chosen to eat elsewhere that day, but rather about the conspicuous absence of extraterrestrial civilizations from a universe that, by all reasonable estimation, should have been teeming with them. Enrico Fermi had won the Nobel Prize in Physics in 1938 for his work on induced radioactivity and the discovery of new elements produced by neutron bombardment, and he had subsequently played a central role in the development of the atomic bomb, having overseen the construction of the first nuclear reactor beneath the stands of a football stadium at the University of Chicago. But beyond these specific achievements, Fermi was renowned among his peers for a particular mental facility that would later become known as the Fermi problem, the ability to make remarkably accurate estimates of quantities that would seem at first glance to be unknowable or at least very difficult to determine. He could calculate, using only basic physical principles and reasonable assumptions, the approximate number of piano tuners working in the city of Chicago, or the volume of water in a swimming pool glimpsed from a distance, or the energy released by a nuclear explosion observed from miles away. This gift for rapid and reliable estimation made his question about extraterrestrial visitors more than idle speculation, for it carried with it the implicit assertion that he had already performed some mental arithmetic and found the expected answer and the observed reality to be in sharp disagreement. The calculation that Fermi would have performed, whether explicitly at that lunch table or in the quiet chambers of his mind during the walk over, proceeds from a set of straightforward observations about the nature of the galaxy in which we find ourselves. The Milky Way, that faint band of light that stretches across the night sky and resolves through a telescope into countless individual stars, is approximately 13.6 billion years old, having formed not long after the universe itself emerged from the primordial conditions of the Big Bang. The Sun, by comparison, is only about 4.5 billion years old, which means that the galaxy had been producing stars for more than 9 billion years before our own solar system condensed from a cloud of gas and dust. During those 9 billion years, countless other stars formed and aged and died, and around many of them there would have been planets, and on some of those planets the conditions might have been suitable for life, and on some fraction of those life-bearing worlds, intelligence might have arisen, and some portion of those intelligent species might have developed technology and looked outward toward the stars. Even if the emergence of technological civilization is exceedingly rare, even if only 1 in a million planets that could support life actually develops intelligent beings capable of space travel, the sheer number of opportunities provided by billions of years and hundreds of billions of stars suggests that many such civilizations should have arisen long before humanity took its first tentative steps on the African savanna. And here the calculation becomes particularly striking, for it does not require any assumptions about faster-than-light travel or other technologies that might violate the known laws of physics. Even a civilization that could travel at only 1% of the speed of light, a pace that is ambitious by our current standards but not physically implausible, could cross the typical distances between neighboring stars in a few hundred years or perhaps 1,000. Such a civilization, spreading outward from its home world and establishing colonies that themselves eventually send out further expeditions, would expand through the galaxy in a pattern not unlike the spreading of a population across an uninhabited continent, and the mathematics of such expansion, even at these modest speeds, leads to a remarkable conclusion. The Milky Way galaxy spans approximately 100,000 light-years from edge to edge, a distance that seems almost incomprehensibly vast when measured against human experience, but which becomes more manageable when considered in terms of cosmic time. A civilization traveling at 1% of the speed of light and establishing new colonies that then wait some reasonable period, perhaps 1,000 years, before sending out their own expeditions, would require something on the order of 10 million years to spread across the entire galaxy. 10 million years is a span of time that defies easy human comprehension, being roughly twice as long as the entire existence of the genus Homo. And yet when set against the 13.6 billion-year history of the Milky Way, it amounts to less than 0.1% of galactic time. The galaxy has had enough time to have been colonized completely not once but more than 1,000 times over, each wave of colonization having had ample opportunity to spread to every corner of the stellar disk before the next civilization even emerged. This was the calculation that gave weight to Fermi's question. The recognition that even under conservative assumptions about the rarity of life and the difficulty of interstellar travel, the galaxy should by now be thoroughly inhabited. And yet we see no evidence of this habitation. The Earth has existed for 4.5 billion years. Its position in space clearly marked by the presence of a blue world with liquid water and an oxygen-rich atmosphere. And during all that time no visitor has left any unmistakable sign of their presence. No artifact buried in ancient strata. No signal beaming from a probe in orbit. No megastructure visible in the sky. The silence is not merely an absence of communication but an absence of any detectable activity whatsoever. A quietness that extends across all the frequencies we have learned to observe and all the timescales we have learned to consider. The lunch at Los Alamos concluded as lunches do, with the participants returning to their various tasks and the conversation fading into the ordinary business of the afternoon. But the question that Fermi had posed did not disappear. It lingered in the minds of those who had heard it and spread gradually through the community of scientists who concerned themselves with such matters, becoming a touchstone for discussions about the possibility of life elsewhere in the universe. For a quarter of a century it remained an informal puzzle, a question passed from person to person without any systematic treatment in the scientific literature. Until in 1975 a physicist named Michael H. Hart published a paper in the Quarterly Journal of the Royal Astronomical Society that gave the problem its formal shape. Hart's paper, titled Explanation for the Absence of Extraterrestrials on Earth, approached the question with the rigor of a scholarly argument, laying out the various possible explanations for the observed absence and evaluating each in turn. It was Hart who gave the paradox its structure as a genuine scientific problem rather than merely a provocative question, and it was in the wake of his publication that the term Fermi Paradox came into common usage, linking the formal analysis back to that casual lunchtime conversation in the New Mexico highlands. The paradox, as Hart formulated it, rests on the tension between the high probability estimates for the existence of extraterrestrial civilizations and the complete lack of evidence that any such civilizations exist, a tension that demands resolution through either a revision of our probability estimates or an explanation for why civilizations that do exist have not made themselves apparent. The numbers involved in the paradox have been refined over the decades since Hart's paper appeared. As astronomers have learned more about the prevalence of planets around other stars and biologists have developed more sophisticated models of the conditions required for life, but the essential structure of the problem remains unchanged. The Milky Way contains somewhere between 100 billion and 400 billion stars, and observations from space telescopes suggest that planets are common, with most stars having at least one world in orbit and many having several. The conditions for life as we understand it, liquid water and a suitable temperature range and the presence of certain chemical elements, appear to be met on a significant fraction of these planets. And while we do not yet know how easily life arises from non-living matter, the sheer number of opportunities suggests that it has likely happened many times throughout the galaxy. And yet the sky remains silent, the Earth remains unvisited, and the paradox that Fermi articulated over lunch in 1950 continues to puzzle those who contemplate our place in the cosmos. The question of where everybody is has not been answered definitively. though many possible answers have been proposed and carefully considered, each offering a different perspective on what sort of universe we might actually inhabit and what the silence might mean for our own future among the stars. The possibilities range from the mundane to the profound, from simple explanations involving the difficulty of interstellar travel to unsettling hypotheses about the fate of civilizations that advance beyond a certain technological threshold. And the exploration of these possibilities occupies a quiet corner of modern astrophysics and astrobiology, a field that proceeds without urgency but with persistent curiosity about one of the deepest questions that human beings have ever asked. In the quiet of the early spring, when the hills of West Virginia were still holding on to the last of the winter chill, a young astronomer named Frank Drake pointed a radio telescope toward the stars and simply listened. It was the 8th of April in 1960, and the world was busy with other concerns, as the world so often is. But in a small observatory nestled in a valley near the town of Green Bank, something rather wonderful was beginning. Drake had constructed what he called Project Ozma, named after the princess Inel. Frank Baum's stories of the land of Ounce, a place that was distant and unknown and filled with strange beings, which seemed fitting enough for an endeavor aimed at detecting signals from civilizations that might exist around other suns. The telescope itself was a modest instrument by later standards, an 85-foot dish that the locals had affectionately nicknamed the Tater on account of its shape resembling something like a potato, though in truth it looked more like a great metal bowl turned toward the heavens. Drake had chosen his targets with considerable care, selecting two stars that were reasonably similar to our own sun and reasonably close to us in the vast distances of the galaxy. The first was Tau Ceti, a star in the constellation of the Whale, sitting about 12 light-years from Earth, which means that any signal we might receive from there would have left its source 12 years before we heard it, traveling all that time at the fastest speed the universe allows. The second was Epsilon Eridani, another sun-like star, this one in the constellation of the River, just a bit closer at about 10.5 light-years away. For 150 hours across the months of April and into the early summer, Drake and his small team sat with their equipment, listening to the radio frequencies that they thought an intelligent civilization might reasonably choose for interstellar communication. The frequency they monitored was near 1420 MHz, which corresponds to the natural emission of hydrogen atoms, the most abundant element in the universe, and therefore a frequency that any technically advanced species would likely be aware of and might select as a kind of cosmic meeting point, a place on the radio dial where minds across the light years might find one another. The work was patient and rather tedious, as so much of science tends to be, involving long stretches of watching instruments and recording data and hoping for something out of the ordinary. And then, rather suddenly, something out of the ordinary did happen. On one of the early observing sessions, the equipment registered a strong signal, a clear and powerful burst of radio energy that seemed to be coming from the direction of one of the target stars. The needles jumped, the recorders scratched their marks, and for a brief and startling interval, it appeared that Project Ozma might have succeeded beyond anyone's reasonable expectations. The excitement in the small control room must have been considerable, though Drake and his colleagues were careful scientists and understood that extraordinary claims require extraordinary evidence. They checked their equipment, they verified their recordings, and they waited to see if the signal would repeat. When they investigated further, they discovered that the source of the mysterious transmission was not a civilization orbiting Tau Ceti or Epsilon Eridani, but rather a high-altitude aircraft passing through the beam of the telescope. its onboard electronics producing radio emissions that had briefly masqueraded as a message from the stars. The signal was entirely terrestrial, entirely mundane, and Project Ozma continued its patient listening without further incidents of note. In the end, those 150 hours yielded no evidence of extraterrestrial intelligence, only the soft hiss of cosmic background noise and the occasional interference from earthly sources. But the project had accomplished something important nonetheless. It had demonstrated that such searches were technically feasible, that we possessed the instruments and the methods to scan the skies for artificial signals, and that the question of whether we are alone in the universe was not merely philosophical but could be approached through the careful application of scientific investigation. Drake had opened a door, and others would follow through it in the years and decades to come. 7 years after Project Ozma concluded, in the summer of 1967, a young graduate student at Cambridge University in England was carefully examining the output of a radio telescope that had been constructed to study a completely different phenomenon. Her name was Jocelyn Bell, and she was working under the supervision of Anthony Hewish, helping to operate a new telescope designed to detect the twinkling of distant radio sources caused by the solar wind. The telescope itself was a sprawling affair, covering nearly 5 acres of English countryside, consisting of more than 1,000 wooden posts connected by over 120 miles of wire and cable, looking rather more like a farmer's attempt at a very ambitious fence than a scientific instrument. Bell's task was to analyze the recordings produced by this telescope, which came in the form of long paper charts covered with the squiggles and traces of the automatic pens. It was meticulous work, requiring her to examine roughly 100 feet of chart paper every day, searching for the subtle variations that might indicate something interesting. And in August of that year, she noticed something peculiar, a bit of what she later called scruff on the recordings, a regular pattern of pulses that did not match anything the telescope was supposed to be detecting. The signal appeared, disappeared, and then appeared again, always from the same patch of sky, always with the same curious regularity. At first, Bell and Hewish considered the possibility that the signal was interference from some earthly source, perhaps electrical equipment or radar or some other technological artifact of human civilization. They checked their instruments, they investigated local sources of radio noise, and they found nothing that could account for the mysterious pulses. The signal persisted, appearing with clockwork precision, each pulse separated from the next by an interval of approximately 1.337 seconds, a regularity that seemed almost too perfect to be natural. As the weeks went on, Bell discovered additional sources with similar characteristics, each pulsing at its own distinct rate, each located in a different part of the sky. The regularity of these signals was astonishing, more precise than the best clocks that human beings had constructed, and for a time, no one could explain what natural phenomenon might produce such behavior. It was during this period of uncertainty that the team at Cambridge gave the first of these sources a rather whimsical designation. They called it LGM-1, with the letters standing for Little Green Men, a half-serious acknowledgement of the possibility, however remote, that they had stumbled upon artificial signals from an extraterrestrial civilization. Bell herself later recalled that she found this possibility rather annoying, as she was in the midst of completing her doctoral thesis and the presence of little green men would be a considerable inconvenience to her academic plans. But as with Project Ozma's false alarm, the explanation proved to be natural rather than artificial, though no less remarkable for being so. What Bell had discovered were pulsars, rapidly rotating neutron stars, the collapsed cores of massive stars that had ended their lives in tremendous explosions. These dense remnants, no larger than a small city but containing more mass than our Sun, spin at extraordinary rates and emit beams of radio energy that sweep across space like the light from a rotating beacon. When such a beam happens to point toward Earth, we receive a pulse, and the incredible regularity of the neutron star's rotation produces the clockwork precision that had seemed so artificial. The discovery of pulsars was one of the most significant astronomical findings of the 20th century, and Anthony Hewish was later awarded the Nobel Prize for his role in the work, though the omission of Jocelyn Bell from that honor remains a subject of considerable discussion among those who study the history of science. But for our purposes, the episode illustrates an important truth about the search for extraterrestrial intelligence, which is that the universe is full of strange and unexpected phenomena, and distinguishing artificial signals from natural ones is a far more difficult task than one might initially suppose. A decade after the discovery of pulsars, on the 15th of August in 1977, a volunteer researcher named Jerry Ehrman was examining computer printouts from a radio telescope operated by Ohio State University. The telescope was called Big Ear, a name that described both its function and its appearance, consisting of a large flat reflector that collected radio waves and directed them toward the receiving equipment. Big Ear was engaged in a systematic survey of the sky, part of an ongoing search for extraterrestrial signals, and Ehrman had been reviewing the data several days after it was collected, looking for anything unusual amid the constant flow of cosmic noise. What he found, printed on the output from the night of August the 15th, was a signal unlike anything the telescope had recorded before. It appeared as a sequence of characters indicating the intensity of the radio emission at successive intervals, and the signal rose rapidly in strength, peaked at a remarkable level, and then faded away again, all over the course of approximately 72 seconds. The duration matched precisely what would be expected from a signal coming from deep space, as the telescope's field of view swept past a fixed point in the sky due to Earth's rotation. The frequency was very close to the hydrogen line that Frank Drake had monitored in Project Ozma, suggesting that if this were an artificial signal, its creators had chosen the same cosmic meeting place that human scientists had long considered the most logical choice. Ehrman was so struck by what he saw that he circled the relevant characters on the printout and wrote a single word in the margin, an exclamation of surprise that would give the detection its name in the years that followed. The signal became known by that annotation as a remarkable anomaly that has never been satisfactorily explained. In the days and weeks that followed, Big Ear was turned back toward the same region of sky again and again, but the signal did not repeat. Other telescopes joined the search, scanning the same coordinates with even more sensitive equipment, and they too found nothing. Whatever had produced that 72-second burst of radio energy had either moved on, switched off, or been something other than what it seemed. Various explanations have been proposed over the years to account for the observation. Some researchers have suggested that it might have been an interstellar signal that was transmitted only briefly, perhaps a beacon that sweeps the sky and illuminates each direction only occasionally. Others have proposed more mundane possibilities, including reflections from space debris or classified satellites. In 2017, an astronomer named Antonio Paris published a paper suggesting that the signal might have been produced by hydrogen gas surrounding a comet that happened to be passing through the telescope's field of view at the time of the observation. This hypothesis remains controversial, with some researchers finding it plausible and others pointing out difficulties with the details. and so the origin of the signal remains officially uncertain. A curious footnote in the history of the search for extraterrestrial intelligence. In 1984, a group of researchers who had been involved in various aspects of the search decided to establish a dedicated organization to continue and expand this work. They founded the SETI Institute, with those letters standing for the Search for Extraterrestrial Intelligence, and based it in California, where it could draw upon the technical resources and scientific expertise of the region. The institute would go on to conduct numerous searches over the following decades, developing new instruments and new strategies, training new generations of researchers, and keeping alive the question that Frank Drake had first asked with his modest telescope in Green Bank. One of the Institute's most ambitious projects was the construction of a new radio telescope specifically designed for the search, a facility that would allow continuous monitoring of vast numbers of stars simultaneously. This became the Allen Telescope Array, named after Paul Allen, who provided much of the funding for its construction, and located at Hat Creek in Northern California, amid the volcanic landscape beneath the shadow of Mount Shasta. The array consists of 42 separate dish antennas, each about 20 feet in diameter, working together as a single instrument that can observe multiple targets at once. It began scientific operations in 2007 and has been scanning the skies ever since, adding its observations to the ever-growing catalogue of places we have looked and listened. And yet, despite all these efforts, despite Project Ozma and Big Ear and the Allen Telescope Array, despite the work of hundreds of researchers over more than 6 decades, despite scanning millions of star systems across a significant fraction of our galaxy, we have found nothing that we can definitively attribute to another intelligence. The universe, as far as our instruments can determine, remains silent. The cosmic radio dial contains only the natural emissions of stars and galaxies and the remnants of stellar explosions, all of it fascinating to astronomers but none of it bearing the unmistakable signature of a mind like our own. This silence is itself a kind of data, a piece of evidence that must be fitted into our understanding of life and intelligence and the possibilities of the cosmos. And it is to the implications of this silence that we shall gently turn our attention, in good time, as our exploration continues. For most of human history, the planets circling other stars were purely theoretical objects, suspected to exist by those who reasoned that our Sun was merely one of countless stars and therefore might not be unique in hosting worlds of its own, but never observed, never confirmed. Never anything more than a reasonable assumption held by astronomers who had no means of testing it. The stars were simply too far away, and any planets accompanying them would be far too dim and far too close to their parent stars to be seen directly, lost in the overwhelming glare like fireflies hovering beside searchlights. It seemed, for a very long time, that we might never know whether other planetary systems existed at all, or whether our own solar system represented some cosmic anomaly, a rare arrangement of matter that had somehow come together around an ordinary yellow star in an unremarkable arm of an unremarkable galaxy. This uncertainty persisted through decades of technological advancement, through the construction of ever larger telescopes and ever more sensitive instruments, until finally, in the autumn of 1995, 2 astronomers working at an observatory in the south of France announced a discovery that would transform our understanding of the universe and deepen the mystery of cosmic silence in ways that no one had quite anticipated. Michel Mayor and Didier Queloz were working at the Haute-Provence Observatory, a modest facility nestled among lavender fields and limestone hills approximately 90 kilometers north of Marseille, when they detected the first confirmed planet orbiting a Sun-like star beyond our own solar system. The star was called 51 Pegasi, visible to the naked eye in the constellation Pegasus, located roughly 50 light-years from Earth, close enough to be considered a neighbor in galactic terms yet impossibly distant by any human measure of distance. The planet they found, which came to be known as 51 Pegasi b, was nothing like what most astronomers had expected the first exoplanet discovery to reveal. It was a gas giant, similar in mass to Jupiter, but it orbited its star at a distance so close that it completed one full orbit in just 4.2 days, racing around 51 Pegasi at a velocity that seemed almost reckless compared to the stately procession of planets in our own solar system. Jupiter, by comparison, requires nearly 12 years to complete a single orbit around the Sun, moving slowly through the outer reaches of our planetary neighborhood, while this new world whipped around its star more than 80 times in the span of a single Earth year. The discovery was unexpected because the theories of planetary formation that prevailed at the time suggested that gas giants could only form in the cold outer regions of stellar systems, where volatile compounds could condense and accumulate into massive atmospheres, and therefore no one had anticipated finding a Jupiter-sized world so close to its parent star that its surface temperature would exceed 1,000 degrees. This new category of planet came to be called a hot Jupiter, and its existence forced astronomers to reconsider their assumptions about how planetary systems form and evolve, opening the possibility that planets might migrate inward after their formation, spiraling closer to their stars through gravitational interactions with the disk of gas and dust from which they emerged. Mayer and Quilloz had not seen the planet directly, of course, as direct imaging of exoplanets remains extraordinarily difficult even today, but had instead detected its presence through the subtle wobble it induced in its parent star, a tiny back-and-forth motion caused by the gravitational tug of the orbiting planet, which shifted the wavelength of the starlight in a rhythmic pattern that revealed the presence of an unseen companion. This technique, known as radial velocity measurement or sometimes as the wobble method, had been refined over many years, and Mayer and Quilloz had developed instruments sensitive enough to detect stellar movements of just a few meters per second, slow enough that a person could outpace them on a bicycle, yet sufficient to betray the presence of a massive planet pulling on its star. The announcement of their discovery was met with some initial skepticism, as extraordinary claims require extraordinary evidence. But within weeks, other astronomers had confirmed the detection using independent observations, and the era of exoplanet discovery had officially begun. Mayer and Quilloz would eventually receive the Nobel Prize in Physics for this work, sharing the honor in 2019. Nearly a quarter-century after their initial discovery, by which time the number of known exoplanets had grown from 1 to thousands, transforming the question of whether other worlds exist into the far more interesting question of just how many there might be and what forms they might take. The true explosion in exoplanet discoveries came not from ground-based observatories like Haute-Provence, but from a spacecraft designed specifically to search for other worlds, launched from Cape Canaveral on the 6th of March, 2009, aboard a Delta II rocket that carried it into an Earth-trailing orbit around the Sun. The Kepler Space Telescope, named after the 17th-century astronomer Johannes Kepler, who first described the mathematical laws governing planetary motion, was equipped with a photometer of unprecedented sensitivity, capable of detecting changes in stellar brightness as small as 20 parts per million, which is roughly equivalent to noticing the dimming of a car headlight when a fruit fly passes in front of it. The telescope was designed to employ the transit method of planet detection, which relies on the simple principle that when a planet passes between its star and our line of sight, it blocks a tiny fraction of the starlight, causing a brief and measurable dip in brightness that repeats with each orbital period. Kepler was pointed at a single patch of sky in the constellations Cygnus and Lyra, a region chosen because it contained a dense field of stars at distances that made them good candidates for transit observations. And there it stared, continuously and patiently, for more than 4 years, monitoring the brightness of approximately 150,000 stars simultaneously, watching for the telltale dimming that would indicate the passage of a planet across a stellar disk. The data that accumulated from this sustained observation was staggering in its volume and its implications, revealing that planets were not rare exceptions but common features of stellar systems throughout our galaxy. Before its primary mission ended due to the failure of 2 of its 4 reaction wheels, the stabilizing gyroscopes that allowed it to maintain its precise pointing, Kepler had confirmed the existence of more than 2,600 planets, with thousands more candidates awaiting verification, and the statistical analysis of its data suggested that there were more planets in the galaxy than there were stars, perhaps 200 billion planets in the Milky Way alone, with a substantial fraction of them orbiting within the habitable zones of their parent stars. The habitable zone is a concept that predates the exoplanet era, having been first articulated by the Chinese-American astrophysicist Su Huang in 1959, when he published a paper describing the region around a star where conditions might permit liquid water to exist on a planetary surface. Huang recognized that liquid water, which is essential for all known forms of life, requires a relatively narrow range of temperatures to persist, and that this range corresponds to a specific distance from any given star, depending on that star's luminosity and temperature. Too close, and water would boil away into vapor; too far, and it would freeze into ice, but at just the right distance, in what is sometimes informally called the Goldilocks zone, water could remain liquid on a planetary surface for billions of years, providing the stable medium in which the complex chemistry of life might unfold. The boundaries of this zone vary considerably depending on the characteristics of the star in question, with cooler red dwarf stars having habitable zones much closer to the stellar surface than the hotter yellow and white stars, and the concept has been refined over the decades to account for atmospheric effects, orbital eccentricity, and other factors that influence surface conditions. Among the thousands of worlds discovered by Kepler, some stood out as particularly interesting from the perspective of habitability, and one of these was Kepler 442b, announced in January of 2015 as one of the most Earth-like planets yet discovered. Kepler 442b orbits a star somewhat cooler and smaller than our Sun, located approximately 1,120 light-years from Earth in the direction of the constellation Lyra, completing one orbit every 112 days at a distance that places it well within the habitable zone of its parent star. The planet is somewhat larger than Earth, with a radius estimated at roughly 1.3 times that of our own world, and while we cannot yet determine its composition with certainty, its size suggests that it is likely a rocky world rather than a gas giant, with a surface where liquid water could potentially exist if atmospheric conditions permit. The discovery of Kepler 442b and similar worlds demonstrated that Earth-sized planets in habitable zones were not merely theoretical possibilities but actual objects, real worlds orbiting distant suns, places where the conditions for life as we understand it might conceivably be met. Another remarkable system emerged not from Kepler's data but from observations made with a much smaller telescope, a 60-centimeter instrument located at the La Silla Observatory in Chile's Atacama Desert. operated by a Belgian-led consortium and given the whimsical name TRAPPIST, an acronym that stands for Transiting Planets and Planetesimal Small Telescope, but also honors the Trappist order of monks who have long been associated with the brewing of Belgian beer. In February of 2017, astronomers announced that this modest telescope, working in conjunction with larger instruments around the world, had discovered a system of 7 Earth-sized planets orbiting a single star just 40 light-years from Earth, a red dwarf known as TRAPPIST-1. The star itself is barely larger than Jupiter, cool and dim compared to our Sun, emitting most of its light in infrared wavelengths, and the 7 planets orbit so close to it that the entire system would fit comfortably inside the orbit of Mercury, with the innermost planet completing an orbit in just 1.5 days and the outermost in approximately 19 days. At least 3 of these planets, and possibly more, appear to lie within the star's habitable zone, making the TRAPPIST-1 system one of the most promising targets for the search for potentially habitable worlds, a place where multiple rocky planets exist at distances where liquid water might persist on their surfaces. The discovery of so many planets in such a compact configuration, all of them similar in size to Earth, captured the imagination of scientists and the public alike, though it also raised questions about the suitability of red dwarf systems for the development of life, as planets orbiting so close to their stars would likely be tidally locked, with one hemisphere in perpetual daylight and the other in eternal darkness, and would be subjected to intense stellar flares that might strip away their atmospheres over time. These questions remain open, subjects of ongoing research and debate, and they remind us that habitability is a complex concept that involves far more than simply being at the right distance from a star. The study of exoplanet atmospheres, which was once thought to be beyond our technological capabilities for decades to come, has advanced more rapidly than expected, particularly since the launch of the James Webb Space Telescope in December of 2021. This instrument, the largest and most powerful space telescope ever constructed, with a primary mirror 6.5 meters in diameter and instruments sensitive to infrared wavelengths that allow it to peer through cosmic dust and analyze the light filtering through distant planetary atmospheres, has begun to reveal the chemical compositions of worlds orbiting other stars. In September of 2023, observations from the James Webb Space Telescope detected the presence of water vapor, along with carbon-bearing molecules, in the atmosphere of a planet called K2-18b, a world roughly 8 times the mass of Earth orbiting within the habitable zone of a red dwarf star some 120 light-years away. The planet is classified as a sub-Neptune, larger than Earth but smaller than the ice giants of our own solar system, and the detection of water vapor in its atmosphere suggests the presence of conditions that might support some form of chemistry conducive to life, though the planet itself is likely very different from Earth in its structure and surface conditions. These discoveries, accumulating year after year, have fundamentally changed our understanding of the universe and the place of planets within it. Where once we knew of only 8 planets, all of them in our own solar system, we now know of more than 5,000 confirmed exoplanets, with thousands more awaiting confirmation, and statistical analyses suggest that the total number of planets in our galaxy alone must number in the hundreds of billions. Rocky planets in habitable zones are not rare anomalies but common outcomes of the processes that form stars and planetary systems, present around a significant fraction of all stars, which means that the galaxy is filled with worlds where the basic conditions for life as we understand it might conceivably exist. The raw materials for life, the carbon and oxygen and nitrogen and water that compose living things, are abundant throughout the cosmos, forged in the cores of ancient stars and scattered through interstellar space by supernovae, and the environments where those materials might assemble into self-replicating systems appear to be present on countless worlds orbiting countless stars in every direction we look. And yet, despite this abundance, despite the billions of potentially habitable worlds that must exist in our galaxy alone, despite the billions of years that have been available for life to arise and evolve and develop technology and spread among the stars, we have detected no signals, no artifacts, no evidence of any kind that any other intelligence has ever existed anywhere in the observable universe. The silence persists. The great emptiness that Fermi noted over his lunch at Los Alamos has only grown more puzzling as our knowledge of exoplanets has expanded, because each new discovery makes the absence of evidence for extraterrestrial intelligence more difficult to explain by simple rarity. If planets are common, and habitable planets are common, and the ingredients for life are common, then life itself should be common, and intelligent life should have arisen many times over the long history of the galaxy, with plenty of time for at least some of those intelligences to develop the means to make their presence known across interstellar distances. The universe, it seems, should be teeming with life, buzzing with signals, marked by the works of countless civilizations, and yet it remains, as far as we can tell, utterly and profoundly silent. A mystery that only deepens with each new world we discover orbiting a distant sun. And so we come now to a concept that has occupied a great deal of quiet thought among those who study the question of cosmic silence, a framework that attempts to explain why we might look out at a universe so vast and ancient and find no clear evidence of other minds, no signals in the static, no monuments on distant worlds, nothing but the patient light of stars burning on in what appears to be an empty and unhurried darkness. In 1996, an economist and researcher named Robin Hanson published a paper with a rather evocative title, The Great Filter, and the subtitle posed a gentle but important question: are we almost past it? Hanson was not the first to wonder why the universe seemed so quiet, as we have already discussed the thinking of Enrico Fermi and others who came before, but he offered a particular way of framing the problem that has proven useful in the decades since, a way of thinking about the question that organizes our uncertainty into something resembling a map, even if that map remains largely blank and speculative. The idea is this, and it is worth taking slowly because it touches on matters both scientific and philosophical. If we consider the journey from raw matter, from hydrogen and helium and the heavier elements forged in the hearts of dying stars, all the way to a civilization capable of spreading across the galaxy, colonizing other worlds, building structures large enough to be seen across interstellar distances, or simply sending signals that could be detected by radio telescopes on distant planets, that journey must contain a great many steps. Hanson suggested that somewhere along this path, there must be at least one step, and perhaps several, where the probability of success is vanishingly small. So small that even given hundreds of billions of galaxies and hundreds of billions of stars within each galaxy and billions of years of time, the number of civilizations that complete the entire journey and become visible to us remains close to zero, or perhaps exactly zero, which would explain why we have detected nothing. This improbable step, or these improbable steps, Hanson called the Great Filter. The filter is whatever it is that prevents dead matter from eventually producing galaxy-spanning civilizations. The filter could be behind us, meaning that we have already passed through the most improbable stages of development and are now among the rare survivors, the lucky ones who made it through. Or the filter could be ahead of us, meaning that civilizations like ours arise with some frequency across the cosmos but are then destroyed or arrested in their development before they can become visible on galactic scales, before they can spread beyond their home worlds and persist through the ages. Let us consider some of the candidate filters that researchers have proposed, taking them gently and without any certainty, as possibilities to be weighed rather than conclusions to be accepted. Each of these represents a stage in the long development from chemistry to civilization, and each presents its own difficulties and its own uncertainties. The first and perhaps most fundamental candidate is the origin of life itself, what scientists call abiogenesis, the transition from non-living chemistry to the first self-replicating systems that could be called, even in the loosest sense, alive. We know that life arose on Earth, and we know that it arose relatively early in our planet's history, within perhaps the first billion years after the Earth formed, possibly much sooner, but we do not know how it happened, and we have not been able to replicate the process in our laboratories despite decades of patient work. In 1952, a young graduate student named Stanley Miller, working in the laboratory of Harold Urey at the University of Chicago, conducted a famous experiment in which he attempted to simulate the conditions of the early Earth. He filled a flask with water and a mixture of gases that were thought to represent the early atmosphere, methane and ammonia and hydrogen and water vapor, and he subjected this mixture to electrical sparks meant to simulate lightning. After running the experiment for several days, Miller found that the water had turned pink and then brown, and when he analyzed its contents, he discovered that it contained amino acids, the building blocks of proteins, the molecules that do much of the work in living cells. This was an exciting result, and it suggested that the raw materials for life might form readily under the right conditions. But amino acids are not life, and the gap between amino acids and even the simplest self-replicating cell remains enormous and poorly understood. In the 7 decades since the Miller-Urey experiment, researchers have made progress in understanding prebiotic chemistry, the chemistry that might have preceded life, but no one has yet created life from scratch in a laboratory. No one has taken simple chemicals and coaxed them into forming a self-replicating system capable of evolution. This does not mean it cannot be done, and it does not mean that abiogenesis is impossibly rare, but it does mean that we cannot yet say how difficult this first step truly was, and it remains a plausible candidate for one component of the Great Filter. Another candidate filter, one that is often overlooked because it seems so technical and biological, is the transition from prokaryotic cells to eukaryotic cells. Prokaryotes are the simple cells that bacteria and archaea possess, cells without a nucleus, without the complex internal structures called organelles, and prokaryotes were the only form of life on Earth for an immensely long time, perhaps 2 billion years or more. Eukaryotic cells, the kind that make up plants and animals and fungi and protists, are far more complex, with a nucleus containing their genetic material, with mitochondria that generate energy, with an elaborate internal architecture that allows for specialization and complexity. The current scientific understanding is that eukaryotes arose through a process called endosymbiosis, in which one prokaryotic cell engulfed another and the two formed a partnership that became permanent, the engulfed cell eventually becoming the mitochondrion. But this transition appears to have happened only once in the entire history of life on Earth, and it took an extraordinarily long time to occur, roughly half of Earth's entire history passing before the first eukaryotes appeared. This suggests that the transition may be genuinely difficult. That the right conditions and the right cellular partners coming together in the right way may be a rare event even on planets where life has arisen. And so the leap to complex cells could be another part of the great filter. Multicellularity is yet another candidate. For most of Earth's history, life consisted of single-celled organisms, each cell living its own life, reproducing on its own, a world of microscopic individuals. The transition to multicellular life, where many cells cooperate to form a single organism with specialized tissues and organs, opens up vast new possibilities for complexity and size and behavior, but it too represents a significant evolutionary challenge. Interestingly, multicellularity has evolved independently on Earth at least 40 times by current estimates, perhaps more, arising separately in plants and animals and fungi and various groups of algae and other organisms, which suggests that this particular transition may not be especially difficult, may not be a strong component of the filter, but the uncertainty remains. And then there is the evolution of intelligence, or more specifically, the evolution of technological intelligence, the kind of intelligence that builds radio telescopes and launches spacecraft and wonders about the silence of the cosmos. Life on Earth has existed for roughly 4 billion years, and in that time, a tremendous diversity of organisms has evolved, from bacteria to blue whales, from slime molds to sequoias, creatures that fly and swim and burrow and climb, organisms of stunning beauty and remarkable adaptation. And yet in all that time and among all those billions of species, only one has developed technology, only one has built civilizations and written books and looked up at the stars with instruments designed to detect the presence of others. This suggests that technological intelligence may be genuinely rare, that evolution does not inevitably produce minds like ours, that we may be a statistical anomaly, a fluke, a fortunate accident that need not be repeated elsewhere even on planets teeming with life. The philosopher Nick Bostrom, who has written extensively on existential risks and the future of humanity, made an observation about the great filter that has become well known in these discussions. Bostrom pointed out that when considering whether the filter lies behind us or ahead of us, the discovery of extraterrestrial life would actually provide evidence, and the nature of that evidence would depend on what kind of life we found. If we were to discover, for example, that Mars once harbored microbial life, fossils of ancient bacteria in Martian rocks, this would be, in Bostrom's framing, bad news for humanity. It would be bad news because it would suggest that the origin of life is not especially difficult, that life arises readily on suitable worlds, and if life arises readily, then the filter that keeps the universe silent must lie somewhere further along the path, somewhere that we have not yet reached. It would mean that the filter is ahead of us, not behind us, and that the silence of the cosmos is explained not by the rarity of life's origin but by some catastrophe or barrier that prevents technological civilizations from persisting or spreading. Conversely, if we explore Mars and the moons of Jupiter and Saturn and find them sterile, lifeless, without even the simplest microbes, this would be, in a strange way, good news, because it would suggest that abiogenesis is difficult, that the first step in the journey is the rare one, and that we have already passed through the most challenging stage of the filter. Another framework for understanding the apparent rarity of civilizations like our own comes from the work of Peter Ward, a paleontologist, and Donald Brownlee, an astronomer, who together wrote a book published in the year 2000 called Rare Earth. And in this book they argued that while simple microbial life might be common in the universe, complex life, multicellular life, animal life, intelligent life, might be extraordinarily rare, not because of any single factor but because of the accumulation of many factors, each of which might be necessary and none of which might be particularly common. Ward and Brownlee pointed to a number of features of the Earth that might be unusual and that might have been necessary for the development of complex life. Our Moon, for example, is unusually large relative to the size of our planet, and its gravitational influence helps to stabilize the tilt of Earth's axis, preventing the wild swings in climate that might occur if our axis wobbled more dramatically over time. This stability may have been important in allowing life to adapt and flourish over billions of years without being subjected to extreme and unpredictable changes in temperature and seasons. They also noted the role of Jupiter, the giant planet in our outer solar system, whose immense gravity may serve as a kind of cosmic shield, deflecting or capturing comets and asteroids that might otherwise rain down on the inner planets with greater frequency, causing mass extinctions and preventing complex life from gaining a foothold. The presence of such a large planet in the right orbital position may be necessary for the long-term survival of complex ecosystems, and such configurations may not be universal. Plate tectonics, the slow movement of Earth's crustal plates, is another factor they considered. This geological activity recycles carbon and regulates the planet's temperature over long time scales through a process involving the weathering of rocks and the burial of carbon in ocean sediments. Without plate tectonics, a planet might fall into a runaway greenhouse effect like Venus or freeze into a permanent ice age, and the presence of active plate tectonics may depend on specific conditions of planetary size and composition and internal heat that are not guaranteed elsewhere. Even our position within the galaxy may matter. Earth orbits in what some researchers have called the galactic habitable zone, far enough from the dense and active center of the galaxy to avoid excessive radiation from supernovae and other violent events, but close enough that the heavier elements necessary for rocky planets and complex chemistry are available. Stars that orbit too close to the galactic center, or that pass through the spiral arms too frequently, may subject their planets to sterilizing radiation or gravitational disruptions that prevent the development of complex life. Ward and Brownlee did not claim that complex life is impossible elsewhere, only that it may be far rarer than simple optimistic calculations would suggest, that the Earth may be an unusual world in an unusual location with an unusual history, and that the silence of the cosmos may reflect this rarity rather than any technological self-destruction or deliberate hiding. All of these ideas, the great filter, the various candidate stages where the filter might apply, the rare Earth hypothesis, should be understood as possibilities rather than certainties. We are reasoning with very limited data, with a sample size of 1 when it comes to known biospheres and known technological civilizations, and our conclusions must remain tentative and humble. The filter may be behind us, and we may be among the fortunate few who have passed through, or the filter may be ahead of us. A sobering thought, but one that might motivate greater care in how we manage our own future. Or the entire framework may be missing something important, some factor we have not yet imagined, and the true explanation for the silence may be something else entirely, something we will only understand when we have more data, more observations, more time to think. And so we come now to a quieter corner of this contemplation, a place where we might consider that the silence we have been discussing is not necessarily an absence at all, but perhaps something else entirely, something that invites us to think about the universe and our place within it with a certain gentle curiosity rather than alarm. For there exist a number of alternative explanations, proposed over the decades by thoughtful people, that suggest the great cosmic quiet might have causes we had not initially considered, causes that range from the deliberately protective to the mathematically cautious to the philosophically profound. And each of these ideas deserves our patient attention as we settle further into this peaceful exploration. The zoo hypothesis is one such idea, and it was proposed in 1973 by a researcher named John Ball, who suggested something rather tender when you think about it carefully. Ball imagined that advanced civilizations might indeed exist throughout the galaxy, perhaps in considerable numbers, but that these civilizations have made a collective or individual decision to leave us alone, to observe us from a distance without interference, much in the way that we humans have learned to establish nature preserves and wildlife sanctuaries here on Earth. In these protected spaces, we deliberately refrain from contact with the animals who live there, not because we lack curiosity or capability, but because we have come to understand that observation without interference allows these creatures to exist in their natural state, to develop according to their own rhythms, to live lives that are authentically their own rather than shaped by our presence. Ball's hypothesis suggests that extraterrestrial intelligences, presumably far older and wiser than ourselves, might have reached a similar conclusion about younger civilizations such as our own. They might watch us with interest, with care, perhaps even with a kind of cosmic affection, while choosing to remain hidden behind the trees, so to speak, allowing us to grow and stumble and learn and develop without the complicating influence of contact with beings so far beyond our current understanding. This is a gentle thought, is it not? The idea that the silence might be a form of kindness, a deliberate gift of space and time in which we might find our own way. The universe in this view becomes not an empty void but something more like a vast and carefully tended garden, with patient gardeners who understand that some things must be allowed to grow at their own pace. A rather different perspective emerges from the work of the Chinese science fiction author Liu Cixin, whose trilogy of novels introduced what has come to be known as the dark forest theory, a name that evokes quite a different kind of silence than the zoo hypothesis. In this conception, the universe is imagined as a dark forest at night, filled with hunters who move carefully between the trees, and the fundamental rule of survival in such a forest is that one must never reveal one's position. Liu Cixin's theory draws upon game theory, that branch of mathematics that studies strategic decision-making, and it proposes that civilizations in the cosmos might face an inescapable logical trap. Any civilization that detects another faces a terrible uncertainty, for it cannot know with certainty whether that other civilization is benevolent or hostile, and the stakes of guessing wrong are existential rather than merely inconvenient. In such circumstances, the theory suggests, the safest strategy might be silence, absolute and complete, for any transmission into the void reveals not only that you exist but where you exist, and that information, once broadcast, cannot be retrieved. A civilization considering whether to announce itself must weigh the potential benefits of contact against the possibility that somewhere in the darkness, another civilization might interpret any signal as a threat to be eliminated before it can grow stronger. This is admittedly a somewhat unsettling line of thought, and yet there is a certain mathematical elegance to it, a cold but consistent logic that helps us understand why intelligent beings might choose to remain forever hidden even if they yearn for connection. The silence in this view is not kindness but caution, not a gift but a survival strategy, and the forest remains dark because everyone within it has learned the same hard lesson about the dangers of being seen. Still another possibility was articulated by the physicist and author Stephen Baxter in 2001, And this one asks us to consider something quite philosophically vertiginous in a slow and dreamy sort of way. The planetarium hypothesis suggests that what we perceive as the universe might not be the universe as it actually exists, that we might instead be inhabitants of an extraordinarily sophisticated simulation, one in which the stars we see and the silence we measure are not reflections of cosmic reality, but rather elements of an artificial environment created for purposes we cannot fathom. In this scenario, the sky itself is a kind of projection, a planetarium of unimaginable scale and fidelity, and the apparent emptiness of space might simply be a feature of the simulation rather than a fact about the cosmos beyond it. This is the sort of idea that might keep a person awake if dwelt upon too intensely, but considered gently, it becomes simply another possibility to hold lightly in the mind. Another reminder that our assumptions about what we are perceiving may not always be correct. We need not decide tonight whether we live in a simulation or a genuine universe. For either way, the stars are beautiful and the questions are interesting, and the softness of the pillow beneath your head is real enough for present purposes. The planetarium hypothesis reminds us that explanations for cosmic silence might extend beyond the physical and into the metaphysical, into territories where science and philosophy blur together like watercolors on damp paper. Beyond these larger theoretical frameworks, there exist more practical and technological explanations for why we might not have detected signals from other civilizations. And these explanations carry their own kind of quiet reassurance. Consider, for a moment, the simple possibility that we have been listening on the wrong frequencies, that the cosmic radio dial has so many stations, so to speak, that we might have missed the ones carrying conversation. The electromagnetic spectrum is vast beyond easy comprehension, stretching from the longest radio waves to the shortest gamma rays. And any civilization choosing to communicate would need to select some portion of this spectrum for their transmissions, a choice that might or might not align with our own assumptions about where to listen. This problem was recognized quite early in the history of radio astronomy, and it gave rise to one of the more poetic concepts in the search for extraterrestrial intelligence, a concept known as the water hole. In 1971, a scientist named Bernard Oliver, who was working on a NASA study of potential search strategies, pointed out that there exists a naturally quiet region of the radio spectrum, a kind of peaceful clearing in the forest of cosmic noise, that lies between two frequencies of particular significance. At 1420 MHz, hydrogen atoms emit radiation as their electrons flip from one spin state to another, and hydrogen is of course the most abundant element in the universe. Nearby, at around 1720 MHz, the hydroxyl molecule, which consists of one oxygen atom and one hydrogen atom, also emits characteristic radiation. Between these two markers, the spectrum is relatively free from natural interference, and Oliver noted that hydrogen and hydroxyl together make water, the substance so essential to life as we understand it. He suggested, with a certain whimsical logic, that alien civilizations might converge upon this water hole frequency range for their communications, just as animals on the African savanna converge upon actual water holes to drink, and that we might therefore focus our listening efforts there. This suggestion has influenced search strategies for decades, though of course we cannot be certain that other minds would follow the same reasoning, that they would choose the same poetic wavelengths for their messages. Nikola Tesla, that remarkable inventor and dreamer, believed as early as 1899 that he had detected signals from Mars while conducting experiments in his laboratory in Colorado Springs, rhythmic pulses that he interpreted as attempts at communication. We understand now, with the benefit of more than a century of additional knowledge, that what Tesla almost certainly heard were natural radio emissions from Jupiter, which produces powerful bursts of electromagnetic radiation through the interaction of its magnetic field with its moon Io. Tesla was listening, in his way, but the universe was speaking a language he could not yet translate. There is also the matter of time, that most patient and inexorable of all dimensions, and when we consider the temporal aspects of our search for cosmic companions, we find yet another gentle explanation for the silence. Human beings have been broadcasting radio signals into space for only about a century, which means that our electromagnetic presence, the sphere of radio waves expanding outward from Earth at the speed of light, extends only about 100 light-years in any direction. This seems like a considerable distance when measured against the familiar scales of human experience. But our galaxy alone spans approximately 100,000 light-years from edge to edge, which means that our radio bubble, if we might call it that, has touched only a tiny fraction of the Milky Way's volume. The vast majority of stars in our galaxy remain unaware, in any electromagnetic sense, that we exist at all, for our signals have simply not had time to reach them yet, and their hypothetical responses have not had time to reach us. When we expand our consideration to include the dimension of time more fully, the mathematics of contact become even more contemplative. The Milky Way galaxy is approximately 13 billion years old, give or take a few 100 million years, which provides a tremendous span during which civilizations might have arisen, flourished, and faded on countless worlds. Human technological civilization, by contrast, has existed for perhaps 10,000 years if we are generous in our definition, and our capacity to send and receive interstellar signals has existed for roughly a century. This represents an almost unimaginably brief moment in cosmic history, a single breath in a lifetime that has already encompassed billions of breaths, and it invites us to consider that even if thousands of civilizations have existed in our galaxy over the ages, the chances that any two of them would exist simultaneously, would be awake and aware at the same cosmic moment, might be remarkably small. Imagine, if you will, a vast dark ocean upon which ships occasionally appear, each one lighting a lantern for a brief time before the lantern goes out and the ship disappears beneath the waves. If the ocean is large enough and the ships rare enough and the lanterns brief enough, two ships might never see each other's lights even if thousands of ships have sailed those waters over the ages. The universe, it seems, might be something like this ocean, and we might be one small ship with a newly lit lantern, scanning the darkness for other lights that burned long ago or will burn long after our own has faded. This is not a melancholy thought but simply a factual one, a recognition that timing matters in ways we do not always consider. Despite these various challenges and uncertainties, the search continues, pursued by dedicated scientists using increasingly sophisticated instruments. In 2015, a project called Breakthrough Listen was launched, funded by a $100 million contribution from the investor and philanthropist Yuri Milner, and operated under the guidance of the Berkeley SETI Research Center. This project represents the most comprehensive search for extraterrestrial intelligence ever undertaken, utilizing some of the world's most powerful radio telescopes to survey millions of stars and thousands of galaxies for signs of technological activity. The scientists involved in Breakthrough Listen work with patience and rigor, scanning the heavens systematically, recording vast quantities of data, and developing sophisticated algorithms to sift through the cosmic noise in search of patterns that might indicate artificial origin. Whether they will find anything, no one can say with certainty, and perhaps it does not matter so very much as we drift here toward sleep. The search itself is a kind of lantern, a light held up against the darkness, and whatever its ultimate results, it represents something beautiful about the human spirit. This persistent curiosity, this gentle refusal to accept that we must always be alone. And now, as you settle deeper into rest, let these possibilities swirl softly together. The zoo and the dark forest and the planetarium, the water hole and the radio bubble and the ships upon the ancient sea. All of them simply stories we tell ourselves about the silence. Stories that help us wonder without fear, that help us question without urgency, that help us rest. When we listen for signs of life beyond our own world, we need not limit ourselves to the crackle and hum of radio waves drifting through the cosmos, for there are other ways that a civilization might announce its presence, other signatures that could betray the existence of minds at work among the stars. And over the decades our search has grown to encompass these quieter, subtler forms of evidence, these whispers of light that might tell us we are not alone in the vast and patient darkness. The idea that we might detect a civilization not by its deliberate signals but simply by the consequences of its existence, by the unavoidable byproducts of its engineering and its industry, is an elegant one, and it traces back to a paper published in the year 1960 by the physicist Freeman Dyson, who was working at the Institute for Advanced Study in Princeton, where he had already made significant contributions to quantum electrodynamics and would go on to think deeply about many other problems at the boundary between physics and imagination. Dyson considered a rather straightforward thermodynamic argument, which was that any civilization with sufficient technology and sufficient time would eventually require more energy than its home planet could provide. And the most obvious source of energy in any solar system is, of course, the central star, which radiates an almost unimaginable quantity of light in all directions, of which any single planet captures only the tiniest fraction. Dyson proposed that a sufficiently advanced civilization might construct a swarm of collectors, a vast shell or sphere of structures orbiting their star and capturing its light, converting that energy into useful work before eventually radiating it away as waste heat in the infrared portion of the spectrum. Such a structure, which came to be known as a Dyson sphere or Dyson swarm, would be invisible to optical telescopes looking for the bright light of a star, because that light would be absorbed and utilized, but it would glow warmly in the infrared, a soft and telltale excess of heat where we might otherwise expect to see only the cold darkness between the stars. Dyson himself was careful to note that he was not proposing that such structures definitely existed, only that they were physically plausible and that if they did exist, we could in principle detect them, and this notion opened up an entirely new avenue of inquiry, one that did not depend on another civilization choosing to communicate with us but merely on the laws of thermodynamics applying to their engineering projects as they do to ours. For many years the search for such infrared signatures remained largely theoretical, a speculation discussed in papers and at conferences but not pursued with the systematic rigor that Radio SETI enjoyed. And this was partly because infrared astronomy itself was still developing the tools and techniques necessary for such a survey, and partly because the idea seemed perhaps too speculative, too much like science fiction to merit the allocation of precious telescope time. But as infrared telescopes improved and as surveys of the sky grew more comprehensive, it became possible to look for these signatures in earnest. And one notable effort in this direction was the Glimpsing Heat from Alien Technologies survey, sometimes referred to by the somewhat whimsical abbreviation GHAT, which was led by the astronomer Jason Wright at Penn State University and which made use of data from NASA's Wide Field Infrared Survey Explorer spacecraft. The GHAT survey examined approximately 100,000 galaxies, looking for any that showed an unusual excess of infrared emission relative to their optical light, which might indicate that a significant fraction of the starlight in that galaxy was being captured and re-radiated by vast engineering projects. The survey found no clear evidence of galaxy-spanning civilizations wrapping their stars in energy-collecting structures. And while this null result might seem disappointing, it is itself a piece of information, a constraint on what is possible, a gentle narrowing of the parameter space within which extraterrestrial intelligence might hide. The absence of obvious Dyson spheres in 100,000 galaxies tells us something about the prevalence of such technology, or about its durability, or about whether civilizations that develop such capabilities proceed to use them in ways that would be visible to our instruments. And like so much of this field, the negative result is woven back into our understanding, refining our estimates and guiding future searches. Closer to home, within our own galaxy, the search for individual Dyson spheres has occasionally produced intriguing candidates. And perhaps the most famous of these is the star known by its catalogue designation KIC 846-2852, which came to public attention in the year 2015 and which is more commonly referred to as Tabby's star, after the astronomer Tabitha Boyajian, who led the team that first characterized its unusual behavior. This star, which lies approximately 1,400 light-years from Earth in the constellation Cygnus, was observed by the Kepler Space Telescope as part of its mission to detect exoplanets by watching for the slight dimming that occurs when a planet passes in front of its host star, blocking a small fraction of the starlight from our view. Most such transits produce regular, repeating dips of 1% or so in the star's brightness, predictable patterns that reveal the presence of worlds in orbit. But Tabby's star showed something quite different, something that no one had seen before. The dimming events observed from KIC 846-2852 were irregular, occurring at unpredictable intervals and with unpredictable depths, and some of these dips were far larger than any planet could produce, with the starlight dropping by as much as 22% in certain events, a dimming so profound that it suggested something truly enormous was passing between us and the star. The pattern did not match any known natural phenomenon, not a planet, not a companion star, not the ordinary variations that some stars undergo due to their internal processes. And this mystery captured the attention of astronomers and the public alike, sparking speculation that perhaps, at last, we had found evidence of a Dyson swarm under construction, vast structures being assembled around a distant sun by beings we had never met and could scarcely imagine. The speculation was understandable, even inevitable, given the strangeness of the observations and the long tradition of imagining just such artifacts. But science proceeds by testing hypotheses against further evidence, and as more observations accumulated, a more prosaic explanation began to emerge. Studies of the star's spectrum and of the wavelength dependence of its dimming events suggested that the obscuring material was not solid, not the rigid panels of an engineered structure, but rather a cloud of dust, perhaps the debris from a disintegrating comet or a series of comets, perhaps material from a collision in the star's planetary system, something natural though uncommon, something that did not require the intervention of intelligent beings to explain. The mystery of Tabby's star has not been entirely solved, and there remain details that are not fully understood. But the current consensus favors dust over alien megastructures, and this too is how science works, with initial excitement giving way to careful analysis. with extraordinary claims requiring extraordinary evidence, and with the most parsimonious explanation generally winning out in the end. Beyond infrared surveys and the search for Dyson spheres, there are other ways that light might carry news of distant intelligence to our patient instruments, and one of these involves looking not for the waste heat of energy consumption but for deliberate signals sent using light itself, the focused beam of a powerful laser aimed in our direction by beings who wish to make contact. This approach, sometimes called optical SETI, has certain advantages over radio communication, because a laser can be focused very precisely, delivering far more energy per unit area to a distant receiver than a radio transmitter of equivalent power, and because the brief pulse of a laser, lasting perhaps a billionth of a second, would stand out sharply against the steady glow of starlight, making it relatively easy to distinguish from natural sources. The idea of searching for laser pulses from extraterrestrial civilizations has been pursued for several decades, and one notable program began at Lick Observatory in California in the year 1998, where astronomers developed instrumentation capable of detecting nanosecond flashes of light from nearby stars. This search has examined thousands of stars over the years, looking for brief bright pulses that cannot be explained by natural phenomena, and while no confirmed signals have been found, the search continues, refined and extended by new generations of researchers with ever more sensitive equipment. Similar programs have operated at other observatories around the world, and proposals have been made for even more ambitious efforts, including surveys that would monitor large swaths of the sky continuously, waiting for a flash that might come from any direction, any time, unannounced and unexpected. There are also proposals to search for signs of life that are not deliberate signals at all but merely the chemical consequences of biology, the fingerprints that living processes leave on a planetary atmosphere, and these are known as biosignatures, and they represent a different approach to the question of life beyond Earth, one that does not assume intelligence or technology but merely the existence of organisms going about their metabolic business, breathing and eating and excreting, and in doing so altering the composition of the air above them. On Earth, for example, the presence of oxygen in our atmosphere is largely the result of photosynthesis by plants and cyanobacteria, and this oxygen coexists with methane produced by various organisms. And these two gases should not persist together for long because they react with each other chemically, so their simultaneous presence indicates an active source of both, a planet with ongoing biological activity replenishing what chemistry would otherwise remove. This state of chemical disequilibrium is something we could in principle detect from afar, by analyzing the light that passes through or reflects from a distant planet's atmosphere, and this is precisely what a new generation of telescopes is designed to do. The James Webb Space Telescope, launched at the end of 2021 and now operating at a point far from Earth where it is shielded from our planet's warmth and light, carries instruments capable of studying the atmospheres of exoplanets in unprecedented detail, and among its many scientific objectives is the search for just such biosignatures, the telltale combinations of gases that might indicate life. When a planet passes in front of its host star, a small amount of the starlight filters through the planet's atmosphere before reaching us, and by carefully analyzing which wavelengths of light are absorbed and which pass through, we can determine what molecules are present in that atmosphere. And this technique, called transmission spectroscopy, has already been used to detect water vapor and carbon dioxide in the atmospheres of distant worlds, and the hope is that it might someday reveal oxygen, methane, ozone, or other indicators of biological activity. There are even more exotic possibilities. including the detection of industrial pollution as a sign of technological civilization. And researchers have proposed that molecules such as chlorofluorocarbons, the CFCs that were once widely used in refrigerants and aerosols here on Earth, might serve as technosignatures, because they are not produced by any known natural process and would indicate the presence of an industrial society altering its planet's atmosphere. Such molecules would be difficult to detect at interstellar distances with current technology, but the idea illustrates the breadth of thinking in this field. The willingness to consider any signature that might betray the presence of life or intelligence, and to develop the instruments that might someday make such detections possible. The search for biosignatures has already produced moments of excitement and controversy, and one notable example occurred in September of 2020, when a team led by the astronomer Jane Greaves at Cardiff University announced the detection of phosphine in the atmosphere of Venus, our nearest planetary neighbor. Phosphine is a molecule composed of one phosphorus atom and 3 hydrogen atoms, and on Earth it is produced primarily by microorganisms living in oxygen-free environments, and the presence of phosphine in the clouds of Venus, where conditions are extremely hostile to life as we know it, was proposed as a possible indicator of biological activity. Aerial microbes perhaps floating in the cooler layers of the Venusian atmosphere where temperatures and pressures are less extreme. The announcement generated enormous interest and no small amount of skepticism, and in the months that followed, other researchers reanalyzed the data and questioned the detection, pointing to possible errors in the data processing and to alternative non-biological explanations for the spectral features that had been observed. The debate continues, with some scientists maintaining that the phosphine signal is real and others arguing that it was an artifact of the analysis. And this is precisely how such claims are meant to be tested: through independent verification, through scrutiny and challenge, through the patient accumulation of evidence until a consensus emerges. Whether or not phosphine exists in the atmosphere of Venus, and whether or not it indicates life if it does, the episode illustrates the care with which biosignature claims must be evaluated, and it demonstrates that the scientific community takes such claims seriously enough to subject them to rigorous examination. The detection of life beyond Earth would be among the most profound discoveries in human history, and precisely because of this significance, the standards of evidence are high, and scientists are appropriately cautious about drawing conclusions before the data warrant them. And so the search continues, ever more sophisticated, ever more patient, with new instruments and new techniques expanding the ways we can look for life and intelligence beyond our small world. We listen for radio signals and we watch for laser pulses. We scan the infrared sky for the waste heat of alien engineering, and we analyze the light of distant atmospheres for the chemical signatures of biology. And though we have not yet found what we are looking for, we have not stopped looking. And we will not stop, because the question is too important and the universe is too vast and too old for us to imagine that the answer is simply not there. And so we come now to the end of our quiet journey through the silence, drifting gently toward a place of rest, where the questions themselves become a kind of comfort, and the vastness that once seemed so empty reveals itself to be simply vast, neither hostile nor welcoming, but present, patient, and profoundly beautiful in its indifference. We have wandered through the mathematics of Drake's equation and the paradox that bears Fermi's name. We have considered the filters that might await civilizations and the barriers that might already lie behind us. And now we arrive at a contemplative shore, where uncertainty is not a failure of knowledge but an invitation to wonder, and where the cosmic dark is not a void to fear but a canvas upon which we paint our questions in the soft light of curiosity. the American astronomer and science communicator Carl Sagan, whose voice became synonymous with the gentle exploration of cosmic mysteries, once offered a thought that has echoed through the decades since he first spoke it in his 1980 television series Cosmos. "The universe," he observed, "is a pretty big place. And if it is just us, that seems like an awful waste of space." There is something both humbling and hopeful in those words. A recognition that the sheer scale of existence suggests possibility, that all those billions of galaxies and their hundreds of billions of stars might harbor something, somewhere, that shares our capacity for wonder. And yet the thought contains its own quiet acceptance too, an acknowledgement that we do not know, that we may never know, and that the question itself carries a weight that no answer could fully satisfy. The British writer Arthur C. Clarke, who spent his life imagining the futures that might await us among the stars, offered a complementary observation that has stayed with those who ponder these questions late into the night. There are, he noted, two possibilities regarding the existence of extraterrestrial intelligence, and both of them are equally staggering. Either we are alone in the universe, or we are not alone, and Clarke understood that neither answer offers the comfort of simplicity. To be alone would mean that in all this immensity, across all these light years and all these eons, consciousness emerged only once, here, on this small blue world, and that the responsibility for meaning falls entirely upon our shoulders. To not be alone would mean that others are out there, perhaps watching, perhaps waiting, perhaps utterly indifferent to our existence, and we would need to reckon with what their presence might mean for our understanding of ourselves. Both possibilities stretch the imagination to its limits, and both leave us changed by the contemplation. In the year 1977, as the space age was still finding its footing and humanity was learning to send its machines beyond the familiar confines of Earth, two spacecraft were launched on journeys that would eventually carry them beyond the boundaries of our solar system entirely. Voyager 1 and Voyager 2, twin explorers built of metal and silicon and the accumulated dreams of countless engineers and scientists, were sent outward to study the giant planets, Jupiter and Saturn and, in Voyager 2's case, Uranus and Neptune as well. But someone had the foresight to understand that these machines would not stop at the edge of our planetary neighborhood, that they would continue drifting outward into the interstellar medium, and that they might one day, in some impossibly distant future, encounter something or someone capable of finding them. And so the Voyager spacecraft were equipped with golden records, phonograph recordings encased in gold-plated aluminium covers, designed to survive the harsh environment of space for hundreds of millions of years. These records carry with them a message from Earth, a kind of cosmic message in a bottle, cast into an ocean so vast that the metaphor almost fails to capture its scale. The records contain greetings spoken in 55 human languages, from Akkadian, which has not been spoken as a living tongue for thousands of years, to Wu Chinese, from English to Esperanto, each voice offering a simple hello to whoever might one day listen. They contain the sounds of Earth, the crash of surf and the rumble of thunder, the calls of birds and the songs of whales, those great gentle creatures whose vocalizations carry through the oceans in patterns we still do not fully understand. And they contain music, a selection chosen to represent the breadth of human musical expression, including a performance of Chuck Berry's Johnny B. Good. That exuberant celebration of a country boy who could play a guitar just like ringing a bell, now sailing through the cosmic dark at a speed of roughly 17 kilometers per second. Voyager 1 is now more than 15 billion miles from Earth, a distance so great that light itself, the fastest thing in the universe, takes more than 22 hours to travel from the spacecraft back to us. It has crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, and it is now technically in interstellar space, though it will be tens of thousands of years before it approaches another star. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445, a red dwarf in the constellation Camelopardalis, and though it will not enter that star's planetary system, if any such system exists, it will drift through the neighborhood, carrying its golden record and its message from a species that may or may not still exist by then. The record includes instructions for playback, etched in symbols designed to be decipherable by any intelligence capable of finding the spacecraft in the first place, though whether those instructions will ever be followed, whether any curious mind will ever lower a stylus onto that golden groove and hear the voices of Earth, is something we cannot know and will never learn. Perhaps this is the nature of the Fermi Paradox itself, not a puzzle to be solved but a meditation to be embraced. We have considered so many possible explanations for the silence, from the technical to the philosophical, from the hopeful to the sobering, and yet none of them has proven definitive. None has allowed us to close the book and move on to other questions. And perhaps that is because the question is not really about extraterrestrial intelligence at all, or not only about that, but about us. About what it means to be a questioning species in a universe that does not offer easy answers. About what it means to look up at the night sky and feel both the loneliness and the wonder that such looking inevitably brings. Consider the scale of time and distance that separates us from even our nearest cosmic neighbors. The light that reaches our eyes from the Andromeda Galaxy, that faint smudge visible on clear dark nights, began its journey approximately 2.5 million years ago. When those photons first set out across the void, there were no humans on Earth. Our distant ancestors were still millions of years away from walking upright across the African savannas, still millions of years away from developing the language and the curiosity that would eventually lead to questions about the stars. The universe that Andromeda's light reveals to us is not the universe as it is now, but the universe as it was before we existed. And when the light we might send toward Andromeda finally arrives, 2.5 million years from now, we cannot know what will have become of us, whether our descendants will still be here to receive any reply, whether the question of cosmic loneliness will still trouble whatever minds might then exist. Perhaps the silence is simply this: the natural consequence of vast distance and deep time, the result of messages that are still traveling, of civilizations that rose and fell before we were here to notice, of signals that passed through our solar system when the dinosaurs still walked the Earth, or that will arrive long after we have gone. The universe does not operate on human timescales. It does not arrange itself for our convenience, and the silence that seems so profound to us might be nothing more than the ordinary quiet of a cosmos too large for conversation, a silence that reflects not emptiness but simply distance, the kind of silence you might expect if you stood alone in a vast forest and wondered why no one answered your call, not because the forest was empty but because the forest was so very, very large. And yet, even if we never receive an answer, even if the silence stretches on for centuries and millennia and the question remains forever open, there is something valuable in the asking itself, something that speaks to what we are and what we might become. To peer into the cosmic dark with curiosity rather than fear, to send our messages and our golden records and our radio signals out into the void without any guarantee of reply, to keep asking even when the universe offers no response. This is a kind of cosmic poetry, A verse written not in words but in radio waves and spacecraft trajectories and the patient accumulation of data gathered by telescopes pointed at distant stars. The universe keeps its secrets, as it always has, as perhaps it always will. The silence of the cosmos is not a rebuke but simply a fact, a feature of the reality in which we find ourselves, and we can choose to interpret that silence in whatever way brings us peace. Perhaps there are others out there, separated from us by distances too great to bridge, civilizations that have asked the same questions we ask and received the same silence in reply. Fellow wanderers adrift in their own corners of the cosmic dark. Perhaps we are alone, the sole inheritors of consciousness in a universe that did not need to produce us but somehow did, and the responsibility for meaning falls to us alone. Either way, we are here, we are asking, and the asking itself is a kind of light, a small warm glow in the vastness. Evidence that the universe has produced at least one species capable of wondering about itself. And so we drift peacefully among the stars, wondering, our questions traveling outward at the speed of light, our golden records sailing through the interstellar medium, our telescopes gathering photons that have traveled for millions of years. The silence is vast, but so is the wonder. And both are part of the same great mystery that has accompanied us since our ancestors first looked up at the night sky and asked what those points of light might be. We do not need an answer to find meaning in the question. We do not need certainty to find peace in the contemplation. The universe is what it is, immense and old and largely silent, and we are what we are, small and brief and full of curiosity. And somehow, in the meeting of those two facts, there is something worth treasuring, something worth carrying with us as we drift toward sleep. The stars continue to burn, the galaxies continue to turn, and somewhere out there, Voyager 1 continues its long slow journey toward Gliese 445, carrying its cargo of human voices and whale songs and Chuck Berry's guitar. We cannot know if anyone will ever find it. We cannot know if the silence will ever be broken. But we can know this much: that we asked, that we wondered, that we sent our message into the dark with hope rather than despair. And that, perhaps, is enough. That, perhaps, is the answer we were looking for all along. Not a reply from the cosmos but the discovery that asking was itself a kind of arrival, that the journey was the destination, that the silence was not empty but full of our own small voice, calling out, wondering, and finding in the very act of wondering a peace that no answer could have provided. Rest now, and let the questions drift, and know that the universe, in all its vastness, has made room for you, for your curiosity, for your wonder. The cosmic dark is not a void but a canvas, and your wondering is part of the painting, a brushstroke in the grand composition that no one may ever see in its entirety but that is beautiful nonetheless. Sleep well, and dream of stars, and know that you are part of the asking, part of the poetry, part of the light.